You're listening to a production of the National Media Archive. To learn more or volunteer, go to nationalmediaarchive.com.
Enrico Fermi might have been the luckiest man ever to win a Nobel Prize. At least that's one way to see it. He was Italy's greatest physicist, and at just 24, he'd already become a professor at the University of Rome. The young man had such a commanding presence in his lab that the students who gathered around him had given him a nickname. They called him the Pope. Unlike the real Pope, though, Fermi was broke. Italy's once glorious reign over science had faded since the age of Galileo. When Fermi's team needed a piece of equipment, they didn't order it from some catalogue. They scavenged metal and glass, hammered it together themselves, half-blind with ambition and caffeine. If they needed shielding from the radiation their experiments unleashed, they didn't have heavy doors and lead-lined walls. No, they ran. They sprinted down the corridors, dodging the invisible bullets of decay, hoping to cheat death just one more day. They were trying to do something that for most people sounded impossible. Madness, maybe. They wanted to make a new element. The periodic table of Fermi's time was like a puzzle with missing pieces. Familiar, yes, but with curious gaps that stared back like empty sockets. Look near the middle, you'd find blank spaces waiting for technetium, francium, astatine, promethium. But the biggest voids yawned open at the bottom. There, a whole row and a half, just absent. Everything they knew about elements came from what they could scrape from nature. Gases swirling in the air, metals locked in stone, liquids seeping underfoot. Some of these things are harmless, stable, tame enough to sit in a schoolroom or a jewelry box. Others are more like sleeping beasts. They spit out invisible particles, tiny missiles that slice through skin and blood and bone. Radium did that. Marie Curie pulled radium's secret out of rock and paid for it with her life. Her daughter, Irene, followed her path. She discovered polonium and most likely died from it too. So if you want to understand why Fermi and his crew dashed back and forth like sprinters, maybe you do now. They were playing tag with death every day in the name of discovery. Making a new element. On paper, the idea is straightforward. Add or strip away protons. 1 proton gives you hydrogen. 2? That's helium. 3? Lithium. Walk the ladder 1 rung at a time, keep counting upward. Reach 92 and you've got uranium, the heaviest thing humans had found. But protons are only half the story. Neutrons, those quiet partners, tip the balance. An element's name depends on the proton count alone, but the neutron count changes its soul. Carbon with 6 protons and 6 neutrons, carbon-12, is steady as stone. It will sit unchanged for billions of years. Slip 2 extra neutrons into carbon's core and you get carbon-14. Now it's restless, radioactive. It wants to shed its excess weight. So it does, spitting out a flicker of energy, an electron, a neutrino, transforming 1 neutron into a proton. Beta minus decay. Carbon-14 turns into nitrogen. 1 unstable atom, 1 stray neutron, and you get an entirely new element born from the old. That was Fermi's gamble. Go to the edge of the known world, uranium at 92, and fire neutrons at it. Maybe, just maybe, you can knock it off balance, coax it to spit out an electron and become element 93. Do it again, and you might push it to 94. And then, who knows? But how would you know you'd done it? There's no sign flashing new element discovered. There's no map to follow, no guide. So they ruled things out the hard way. They compared the results to every known element, down to lead at 82 protons. Nothing matched, no known signature. It looked like a dead end or a triumph. Maybe the atom just broke apart and fell back down the ladder. That's called an alpha decay chain, when the nucleus spits out 2 protons, 2 neutrons, dropping step by step down to lead, the heavy stable haven at the bottom. Or maybe, just maybe, they'd made something new. Fermi became an instant hero, draped in the pride of a country desperate for a win. He even got to pick the names. Rome's old symbols loomed large, fascium from the ancient fasces. But the word had become a monster. It was now the banner of fascism, the dark tide swelling under Mussolini's rule. Fermi, careful and quiet, refused. 4 years passed. November 10th, 1938. In Germany, the night of broken glass. In Italy, new laws clawing away at the lives of Jewish families. Fermi's wife, Laura, was Jewish. Her passport perched on the brink of being snatched away. And then the phone rang. 6 in the evening. The Nobel Prize in Physics. They packed their bags for Sweden before the ink dried. They did not come back. America became their new home. And soon after they landed, Fermi learned the truth. He hadn't made elements 93 and 94. He'd done something stranger. He'd cracked an atom in half. The mistake was beautiful. What he thought was an upgrade, a simple bump up the ladder, was a break instead. In Berlin, another team tried the same trick. They saw krypton and barium, way too light for an alpha decay, but together, 36 and 56, you get 92. Uranium, split clean in two, a spark that would light a century on fire. Nuclear fission. By accident, Fermi cracked open the heart of the atom and handed the world its most terrible secret. Overnight, the chain reaction slipped out of the lab and into history. Wars would bend around it. Empires would brace for its promise and its threat. But the race didn't stop there. The table still had blanks and new names waited in the shadows. If Fermi's blunder could change the world, who else would risk their luck to push the boundaries again? That question, unsolved, hungry, pulled others in. Some honest, some not. One man, decades later, would look at the same table and decide to rewrite its edge. Not by mistake, not by luck, but by lying to everyone watching. Look at the table again. Not the neat rows you remember from your school desk. Look at it as a map of every possible combination of protons and neutrons that could ever hold together for even a breath of time. This is the chart the element hunters use, a sea of possibilities, each square a nucleus that might exist or might vanish faster than a blink. The x-axis stretches out with neutrons, the y-axis climbs with protons. Hydrogen down in the corner, one lonely proton. Helium with its 2 protons, 2 neutrons. Then the climb, step by step. Each step a new element, but not every nucleus wants to live. Some are stable, some shake themselves apart before you can even catch them. See those pillars of brown? Those are the stable ones. They stand like rocky islands rising out of deep water. The height of each pillar is the half-life, how long the nucleus can cling to its shape before decay pulls it apart. The taller the pillar, the longer it lives. Light elements like hydrogen, helium, carbon. Early on, there's a simple balance. The line of stability follows where protons and neutrons are equal. 1 to 1. It makes sense. Nature loves symmetry. But keep climbing the chart and the balance tips. For heavier elements, extra neutrons are needed to glue the protons together, to calm their electromagnetic repulsion. That push and pull. The strong nuclear force clutching everything tight. The positive charges trying to fly apart. Beyond calcium, the path tilts. More neutrons, more buffer for the proton's push. That path of stability winds its way up the mountain until it reaches lead. The final fortress before the chasm opens wide. Stray from that path just a bit and you fall into radioactivity. The map turns red first, half-lives in billions of years, then orange. Half-lives in minutes, then blue, seconds. Deep blue? Milliseconds, if you're lucky. Sometimes so brief that even our best machines can't catch it before it's gone. Each decay is like a tide tugging you back to safety. Alpha decay spits out 2 protons and 2 neutrons, jumping you diagonally back down the chart, step by step, until you land on something stable. Beta decay lets you slip sideways, lose a neutron, gain a proton, nudging you to a new square. But the sea always pulls you back. No matter how far you push, you drift back to the shore of stability. Fermi stood at uranium's edge and threw neutrons like pebbles, hoping they'd stick. He reached as far as anyone could see, but new explorers would come, each one pressing deeper, adding more squares to the map, chasing the dream of discovering land no human had ever set foot on. Victor Ninov. His name would ride on the crest of that wave. He claimed he'd reached the far edge, farther than anyone. If true, he'd mapped out a kingdom at the sea's edge. But to understand how he made that claim, you need to meet the ones who tried before him. The captains who built the ships that crossed this sea. The captain. After Fermi moved on to build the first nuclear reactor under the stands of a Chicago football stadium, the hunt for new elements needed a new champion. That champion would come from the sunlit labs of California, Berkeley, the restless forge of American physics. There the cyclotrons spun. A metal ring, 60 inches wide, small by today's standards, but then it was a cathedral of force. It whipped particles in endless circles, magnets humming, until they slammed into uranium targets like cosmic bullets. In that clash of charged fragments, new elements might flicker into being for a heartbeat. One day, the cyclotron did exactly that. A radioactive lump appeared, one that didn't match any known sample. Element 93, Neptunium. The honor of the find went to Edwin Macmillan and Phil Abelson. No parade, no great fanfare. The world was too busy trembling at the rising war to care. And no one wanted to feed the enemy any clues that the secrets of the atom were being unlocked. Macmillan soon found himself drafting into the radar labs, then the Manhattan Project, where the raw fear of the atom's unleashed power would be forged into the bomb. So a chair sat empty in Berkeley's lab, and that's where Glenn Seaborg stepped in. A Swedish name once spelled Sjöberg was Americanized at Ellis Island by a board official who swapped letters like puzzle pieces. The boy who added an extra N to Glenn just because it looked cool would one day sign his name onto the periodic table itself. He wasn't meant to be the hero. He was just a chemist walking across the Berkeley campus when someone from the radiation lab waved him over. Could he help separate some chemical samples? That random tap on the shoulder pulled him into the race. When Macmillan stepped away, Seaborg asked to take the wheel. With war drums echoing across the Pacific, Seaborg got the first crack at element 94. He wasn't working alone. Macmillan had left a recipe behind, a delicate trick of pushing uranium up the ladder. Add one neutron, uranium bumps to neptunium. Slip in a proton too, and the ladder might climb again to plutonium. Plutonium was more than just another square on the map. It was a fuel so potent, so easy to shape into a bomb, that it changed the course of history. Seaborg and his crew packed up their notebooks and their fragile dreams and headed to Chicago, where Fermi waited, the old pope now conjuring chain reactions in makeshift bunkers under the bleachers. Together they squeezed enough plutonium out of battered lab glassware to flatten cities. It was dangerous work. A lead brick cracked a beaker once, soaking up 25% of the world's plutonium supply into a single issue of the Chicago Times. When the bombs fell on Hiroshima and Nagasaki, killing hundreds of thousands and poisoning generations, Seaborg's name was etched into that shadow. But he didn't stop. Back in Berkeley, once the mushroom clouds drifted east, the lab turned back to the map. If 94 was possible, why stop? Plutonium became the new stepping stone. Each neutron fired into its heart might leap the tower higher. 95, 96, berkelium, californium. Names for the lab, for the state that fed its ambition. They even joked they should have named one Universitium Ovium. When they reached 99 and 100, they did it by flying fighter jets through the crown of a nuclear mushroom cloud, scooping radioactive crumbs out of the sky. Those scraps held the seeds of new elements, named for Einstein and Fermi, ghosts in the fallout. Row by row, Berkeley stamped its claim. The New York Times ran headlines, Berkeley discovers half a periodic table. Nobel Prizes followed. Seaborg's name became more than a signature. It became an element. Seaborgium. The captain's flag planted in the radioactive surf. But as Seaborg drifted from lab to White House advising Kennedy sharing whiskey with Johnson, the tides shifted. New captains, new ships. Berkeley wouldn't rule this sea forever. The chart's blanks grew rarer, harder to find. The hunt cost more with every square. And somewhere across the ocean other labs sharpened their knives. They would fight for those last squares on the map. They would gamble lives and reputations on the edge of the nuclear sea. And one man, Victor Ninov, would push that gamble too far. Einstein once said trying to discover new elements was like hunting birds at night in a country with hardly any birds at all. A grim joke, but fitting. By the 1950s and 60s, the easy catches were gone. The periodic table's gaps now lurked at the ragged edge, tiny islands hidden in a rising sea of instability. Finding them meant flinging subatomic projectiles in the dark night after night, month after month, hoping for a hit. Berkeley had the cyclotron and the money, America's Cold War stockpile of brains and budgets. But far across the Iron Curtain, the Soviets watched and waited. Georgy Flerov, the man who guessed America's bomb plan just by reading what scientists didn't publish, turned his mind from war to the hunt. He founded the lab at Dubna, a patch of forest where particle accelerators hummed under frost. Dubna's machines slammed atoms together for Mother Russia, clawing for those elusive elements. In Sweden, a smaller lab claimed element 102. Berkeley and Dubner laughed them off the stage. Your detectors are toys, your proof is thin. They bullied Sweden's claim into oblivion. Then Dubner swooped in, claimed 102, then 103, then 104 and 105. Berkeley fought back with precision. The Soviets preferred spontaneous fission, watching atoms crack open like overripe fruit. Berkeley trusted alpha decay chains, neat step-by-step trails that could be checked and rechecked. Different methods, same goal, be first. The numbers climbed, but the path grew treacherous, the half-lives shrank. By the time you reached element 101, only a handful of atoms existed at a time, ghosts, blinking in and out before you could even weigh them. Shipping samples across continents became impossible. Blink, and your precious target vanished back into lead dust. Then, a flicker of hope. Maria Goeppert-Mayer, the second woman ever to win the Nobel Prize for Physics, saw a pattern in the chaos. Some nuclei she found were like dancers spinning in perfect step, magic numbers of protons and neutrons that locked them into fleeting stability. If the element hunters could hit those magic numbers, they might find an island, a stable shore out in the radioactive sea. An island of stability. The theory said the sweet spot was element 114 with 184 neutrons. No one had ever seen it, but the promise was enough to keep cyclotrons spinning. Years later, Dubner teamed up with Livermore, an American lab. Together they pointed their beam at the island, calcium-48 fired at plutonium-244. And in 1998 they found a tiny foothold, element 114, holding itself together for precious seconds instead of milliseconds. They were close. If the island was real, maybe other stable giants waited in the shallows. Back in Germany, GSI Darmstadt's gleaming lab joined the hunt too. They didn't have Berkeley's legacy or Dubner's stubborn grit, but they had money, the West German economic miracle. New beams, new magnets, new tricks. In a single burst of lucky weeks, they snagged elements 110, 111 and 112. A hat trick. Berkeley, the old king, now watched from the stands. They hadn't found anything new in decades. Enter Victor Ninov. He was Berkeley's secret weapon, stolen from GSI like a prize piece in a chess game. The eccentric Bulgarian with a violin in his hand and hiking boots on his feet. He built software that turned raw detection chaos into readable decay chains, Goosey, his custom code. And only Ninov truly understood it. With him, Berkeley thought they could leapfrog Dubner and GSI, plant their flag on the island of stability first. A Polish theorist, Robert Smolanchuk, gave them the plan. Fire Krypton-86 at lead-208, an improbable shot, the broadside of a barn shrunk to a trillionth. But if it worked, it might land them not just 114, but 108, 2 steps higher than the Russians. So they did it. Easter break 1999. The lab was quiet. Ninov stayed behind, watching the data stream. 11 days later, he told his team, "We did it. 3 perfect alpha decay chains. 118, then 116, then 114. A jackpot." Darlene Hoffman, the lab director, thought she'd missed her chance once before, passed over at Los Alamos, locked out by bureaucracy. Now in her 70s, she could taste the triumph. Ninov's diagram of the decay chain was the prize she'd waited a lifetime for. The press conference crowned Berkeley's return. Their paper splashed Ninov's name at the top. But science is ruthless. GSI, Dubner, Riken in Japan, they all aimed the same beam, ran the same recipe. Nothing, no sign of Ninov's chain. Berkeley's own reruns found nothing. Then, once more, Ninov alone found a new chain. Others using his program saw nothing. Rumours turned to suspicions. Committees formed, notes combed line by line. Goosey's logs held strange glitches, files that no computer could write, event counts too perfect to be chance. In the end, the truth stood clear. Someone had faked it. And only one name fit the fingerprints. Ninov was fired in 2002. His name burned off the map like a smudge. Berkeley's long dynasty ended in shame, and the Cold War of the elements turned cold again. Yet the sea didn't freeze. Dubner and Livermore kept at it, and the island of stability rose from theory to proof. 114, 115, 116, 117, 108, all confirmed in the years that followed. The Russians named the crown jewel Oganesson, after Yuri Oganessian, their living legend, one of only 2 men alive to see their name etched into the table forever. The other? Glenn Seaborg, the captain. There is still an 8th row, somewhere, Maybe 119, maybe 120, maybe element 126, the next magic number, the final island. We build bigger beams, dream up stranger recipes, titanium fired at berkelium, iron smashed into plutonium. Some plans read like a madman's scribble, but that's how it's always been. The periodic table is not just a list, it's a map of how far we're willing to go to touch the edge of what's possible. Some elements cure cancer, some fuel reactors. Most will only ever live for the briefest flicker, vanishing before they can change anything but our understanding. We build these fleeting kingdoms because we can, because the gaps are there, because the sea still calls.